Hi guys, welcome back. This lecture will be mostly taught by Jonas. I'll just be doing the first 5 minutes or so. And we're going to talk about dataset curation and creation. So how do you make a dataset in such a way that you can train the model that you want to train better than if you made the dataset a different way. So are we all on board with what we're going to talk about? We're making data sets. And how do you choose aspects of the data set to make it in a certain way that will make your model better? So that's the focus. Cool. All right, so I want to just remind us of this counts matrix we saw yesterday. So this is that joint distribution called the confident joint, but it's just an unnormalized joint distribution. And can somebody tell me what this 32 would mean in this data set? Like, how would you interpret that 32? Yeah?
There are 32 images that are labeled cow that are actually dogs.
Yeah, estimated, yeah. So there's 32 images that are labeled cow, but they're actually pictures of dogs. Or if this is text, there's 32, text examples about dogs, but they're mistakenly labeled as cow. And so whatever the data set is for these three classes, we've got 32 examples that we've estimated their label given as cow, but they probably should have been labeled dog. Okay, so that's what this thing is. And then we can normalize that and we can get this joint distribution. So we saw that earlier. With this in mind, I want to just look at two motivating examples for data set curation and creation. So imagine that instead you had this matrix here, just as an example. So this is the same, you got your noisy labels. In your classes now, you don't have any information. You're a machine, so they're just numbers to you. 1, 2, 3, 4, 5. And then you guys can see that all the off diagonals are 0, except for 2, the 50s right here. Okay, so the big takeaway, the thing to try to figure out right now is how would you take this data set and try to make it better so you can train a better machine learning model? And yeah.
So you look at the data points that are labeled as third and fourth row, right? And then you order them up in the sort them by the loss function, right? And then you remove the 50 over 250.
Yeah, that's a great approach. So just repeating for the mic and for the recording, but just repeating. So you would take, these 50 examples here. These are things that were labeled a 4, but we think they're a 3. And you would also take these 50 things here that were labeled a 3, but we think they're a 4. And you combine them, and you have these 100 things. And you can get them just by sorting your data that's labeled that we think is or that first, remember the first method where you're automatically finding things that are on the off diagonal? Let's just use that one for simplicity. So we already know what these 50 things are, and then we could remove them from the data set, or we could look at them by hand or using some other tool, and we could relabel them and correct their label. So that would be one way to improve the model. Can anybody think of another way that's very different than what we talked about yesterday? And that has a lot to do with dataset curation. Yeah?
Maybe finding features that we know are unique to one of the two categories, but we know anything about what they could be.
Yeah, I like it. So finding some kind of overlapping feature and using that to make better guesses of the label, something like that?
Or probably better, a feature that doesn't overlap, actually is really good at discriminating the two.
Yeah, totally. So this is an approach actually called labeling functions, and you can use that to get weak and noisy labels. You could take that approach. What about something that you could do to the data set, though, at a higher level? So instead of working with the individual examples, is there anything you could think that you could do with the classes themselves? Yeah?
It seems that it's not confusing almost anything else, so maybe you could say that it should actually be one bigger class that's simple.
Yeah, you could try that, right? And unlike in school where you sort of have a data set and you have to predict 3 or 4, this is your model, You're in control. This is in the real world. This is your data set. If you want to predict a new class that's called 3-4, you could totally do that instead. So now you could have 4 classes, and your machine learning model just predicts 4 classes instead of 5. And then once it's predict one of these classes, you could have some second model that maybe tries to discriminate between the two. There's lots of things you could do. But you could see now if you have this data set and you've merged these 2 classes together, you would have actually no issues in your data, but you didn't have to correct any examples. So you fixed things at the data set level and how you create the data set versus fixing them at the example level. And so that's what we're shifting to in this lecture, is thinking about how do we change the data set. So that's one thing we can do. 2 more quick things. If we change this 50 to a 20, I just want to make sure we understand what this means. So can someone tell me the difference between this one being a 50 and this one being a 20?
Just a smaller misclassification rate for 3 to 4. So you have like a better, with the existing model, you have better ability to, or higher sensitivity in a sense to capture the response that you want.
Yeah, totally.
Precision is higher.
Totally, yeah. So it's a different rate of error in each direction. And that's why we want to use something like what we saw yesterday versus using just like a correlations matrix. So you could totally just do the correlation of every pair of classes. You could have done that, but correlation, that would be symmetric, because correlation is symmetric. So this is more informative than doing a correlations matrix. I just want to make sure we got that idea. And then another idea is to keep in mind is that this means that, for example, if you have a 4, it's more likely to be mislabeled a 3. And when might that happen is when you have a is-a relationship. And I'll show you an example of that. So for example, like a missile is a projectile. And so it's more, or for example, someone from California is from the United States. It's much more likely that someone from California is mislabeled as being in the US than someone from the US being mislabeled as California, because there's 50 states. So you see, like when something is a, you often have this happen. So that's one key idea. Okay, another one is, say that you have, this is the frequency of your classes, all right? And this is another dataset curation trick. And this is usually just called a clutter class. And you'll see this in some datasets. If you have a bunch of, so you've got 4 classes here, and they have a lot of data in them. And then you've got like, I don't know how many, 7, 8, 9 other classes that have just a little bit of data. So you can totally train a model and try to do really well on all of them. Or what some people do, and there's some reasons why this is good, there are some cases where it's not good, but you could, as an option, just thinking from the dataset curation perspective, you could join all these classes together and just make them one class. And so now you have a 5-class problem and call this like the clutter class or something. And now the model just has to say, hey, I've got a lot of data, let me distinguish what these 4 things are. And then once I've done that, I just have to say, is anything else not one of those 4 things? So it's an easier task. And the model's more likely to do an easier task well. And then if it says, hey, this is clutter, you could always train another model. That's like, what is this clutter? What do I think this clutter is? And you could do some kind of pre-training on this and then fine-tuning on whatever you want. There's a lot of approaches to do that accurately. So I just wanted to show, we're starting to think about how do we change the data set. Okay, I just have a few more slides and then I'll pass to Jonas. Any questions? Yeah?
Could you go over one of the columns based on the rows? What do you mean again? Just a view.
Oh yeah, of course. Would someone else like to answer that? So what does like this 12 mean? Yeah?
If you use the confidence learning technique, the 12 means that there's 12 images that are labeled cow, but the confidence learning predictor thinks it's actually a fox.
You got it. So it's just 12 data points that were labeled cow, but they should have been labeled fox. Cool. Okay. So I want to show you ImageNet. We ran this on ImageNet, and I just ranked the off diagonals. So these numbers are from that previous slide, and we've just sorted them in terms of what co-occurs the most. And what you notice, these are actual classes in the ImageNet dataset, and what you'll notice is that noisy label projectile and true label missile is the most occurring pair of classes. And you'll also notice that it occurs down here again, missile and projectile. But you'll see there are more here than here, because again, a missile is a projectile. So you see how that's happening? This is all data driven. There's no like human involvement here. Yeah?
Yeah, were these like normalized for frequency?
No, these are actual counts of errors on the off diagonals, and there's no normalization. So there's a data set. This is the train set, so it's got like 1.3 million examples. And there's 645 examples that were labeled projectile that we think might be missile. And what's really cool about this is it's all automated. And so now you have all the examples that maybe you'd like to merge. And you could bring them together if you, for example, like this is a single labeled data set. So imagine I showed you an image, and the image is of like a missile, okay? So is that a projectile or is it a missile? Because the missile is a projectile. So it's broken. It's actually a broken data set. The way this data set was created that has problems in it. There is no single label that's more true in this case, just because of the is-a relationship. Yeah?
For the seventh row, why is the same label?
Oh yeah. So another thing that's fun that this method reveals is that ImageNet actually has two classes in it that are the same class. That was a mistake. And this just found that automatically. So that's just a mistake in the data set. And it's nice to have that pop up, actually, in an automated fashion. And you can see some more. For example, a bathtub is a tub. That one's very easy. And a cuirass is a breastplate, and a chameleon's a green lizard, and so forth. And so is everybody clear on how this evolves and how you can use this to say, hey, I actually, first of all, I'm discovering that there are issues in my data set. There are some classes that actually are other classes. And maybe I would like to merge those classes, but there's definitely some problems in the way the data set is set up if this is supposed to be single labeled classification. And this automatically reveals that, and then you can change your data set so that you can do better. I would be very confused if I was in class and someone asked me, showed me a picture of a projectile or a missile and said, is this a missile or is it a projectile? It's both. And that's hard for a machine learning model too. And so this is just revealing that you can change the data set and then get a better model. And you can see also the same thing on the ImageNet validation set, like a tape player and cassette player and so forth. And then I wanted to show one final example. This just popped out from ImageNet. And the question is, so these are two classes that were very high up in terms of co-occurring in the confident joint, like on those off diagonals. And can somebody tell me what is the difference between these two classes? Yeah.
Looks like the left one has a curved tail.
Yeah. Very good, yeah. Took me and Anish like an hour to figure that out. Yeah. The beauty of having a crowd of people. So for the microphone, the one on the left has a curved tail. And it's incredible that they're so similar except for just that tiny little thing. And it's up to, of course, the dataset creator and whether the model needs to detect something so fine. But if for whatever the purposes of your machine learning model are, if knowing that curved tail didn't actually have any impact on the task you're trying to do, now you have this automated approach that helps you discover these type of things, and you would merge those classes, and you would have a simpler task that's less confusing. This was certainly confusing for me, at least. Okay, with that, I'll pass it over to Jonas.
Just put this in your pocket. Hi guys. Oh no, I still need the projector, Anish. Yeah. So we learned about basically how we might consider changing the machine learning task just now from Curtis. And for the rest of the lecture, we're going to talk about actually curating the rest of the data set itself. So there's the machine learning task, and then there's the data itself. And so for the rest of this lecture, we're going to focus on sourcing the data and sourcing the labels and common concerns that come up. And so one example of this is to source labels, and most machine learning data sets that have been created, especially for like image classification type of tasks, they're actually labeled by multiple annotators. And how do you work with data that is labeled by multiple annotators? How do you assess the quality of their individual ratings and things like that? And if you're really interested in this subject, I highly recommend the textbook there. It goes into a lot more detail than I will. So some key questions when you're sourcing training data that you should always be asking yourself is, how am I going to actually use the machine learning model? And on what population will this model be making predictions, and at what time? Those are really important questions. And also, what kind of hypothetical edge cases can I imagine where this model might struggle and where we actually really need it to be right, like high-stakes scenarios and rare events. These are all things you should really be thinking about at the time that you're getting the training data, rather than discovering them once you've deployed the model into your application. And so one example I want to get into is, here are two different images of cows. And so this is actually from a real application, and there was a model trained to predict cows. And this model was able to correctly identify that the left image contains a cow, but not the right image. And so does anybody have any guesses why that might have been the case? Yeah, exactly. So there's not many cows at the beach. I mean, it's hard to verify exactly why, because interpretability of models is a whole other subject beyond this class. But that's, if you go look at the training data, you see that there is very few cows on the beach, actually 0 as far as I know. And so this is an example of an issue called the spurious correlation. I think that's it for me, so we can lift the projector. We'll go over here. Yeah, so a spurious correlation is basically a correlation that's present in the data that you're training your model on that does not remain in the data that you're going to deploy your model on, like in the real world. And so if you think about what machine learning models do, they're almost like cheaters that are looking for shortcuts. They're always trying to find what kind of pattern in the training data that you're giving me is highly correlated with the labels. It has no real knowledge about the real world, so any kind of pattern that's present and very predictive of labels, the machine learning model likes to latch onto. And so you need to be really careful about sort of what kind of patterns might be present in a training data set. And so a spurious correlation is a special case of a broader issue in data, which is called selection bias. And really, selection bias is just referring to the broader term of the training data not being fully representative of the real world or the deployment conditions. So more formally, in machine learning, you're always assuming data is coming from an underlying probability distribution. And so here you're just basically, or when you have selection bias in your data set, what it's saying is that the data distribution from which you're drawing your training data doesn't match the distribution in the real world deployment. And this can happen for all kinds of reasons. So can anybody think of some reasons why we might have training data that has selection bias? This is also called confounding or distribution shift. Yeah?
For time series, you might have days that are all older, where you train data, and for deployment, you have newer days where you have different laws of collecting.
Yeah, exactly. So time is like one of the most classic cases that affects sort of any time-based machine learning, where you, by definition, have to collect your training data in the past. And then if you are going to deploy your model today, it will be making predictions in the future. And if the world is changing, there will almost inevitably be some kind of issues that are patterns that may only have been present in the past that no longer remain in the future. That's a big problem in, say, finance and stock market trading. Can anyone else think of any other common causes of selection bias?
Could
Yeah.
the process of looking for the data points that are like mislabeled lead to that issue? Like if we accidentally remove stuff that doesn't need to.
Yeah, so if you remove too much of your data, definitely. So that you could almost imagine as like over curating the data or over filtering it, because you don't want to deal with stuff that's messy, but you actually will see stuff like that in deployment. That's a problem too. Any other common causes people can think of? Yeah?
I can think of an example in automated car training data. It's pretty difficult to collect data about what happens during a crash because it's physically difficult to collect that data.
Yep.
Ease of collecting data.
Yep. Actually, that's two. I'm going to break it into two. So there's rare events that for some reason are just not, there's some mechanism that's preventing these events from making it into your training data. And then the other one was convenience-based collection of training data. And a classic case of this is you are like a grad student and you're doing some kind of survey and you only survey your friends because it's easy. And then one that's kind of similar to time would be location-based. That's a really common one. You know, like you are doing some medical machine learning maybe, and training data comes from like 3 different hospitals, but actually in the future, you want to deploy these models in other hospitals, and there's new kinds of distributions that are emerging there. And so the broader point is selection bias is really, really nasty, and there's basically nothing you can do about it if you don't know any prior knowledge about the form that it will take. And so it's always something to be extremely, extremely concerned about when you're collecting your training data and deciding what data you're going to train on. The one thing you can kind of try and do is to at least evaluate if your model will suffer due to selection bias. And the way to do that is you select your validation data to be most representative of the distribution that you'll expect to see during deployment. So rather than your traditional random training validation split that you might have learned in class, you can actually think carefully about how my data might look different in the future during deployment and try and purposefully select validation data that better represents that, and then remove that from the training data so the training data does not, have those conditions in it, and you can actually see how your model would be suffering under that sort of selection bias. And so an example of doing this for time would be you could just use the most recent data as your validation data. How might we do this for location? Does anybody have any ideas? If there's a location-based selection bias and we actually expect there might be new locations we see during deployment. Yeah?
You could set your validation set so that it's looking at entirely new locations from the training set, so you're testing the distribution.
Yeah, totally. So you can just basically hold out all the data from some locations. What about for the rare events? Anybody have any idea how we could deal with trying to see how our model would do in the presence of rare events? Yeah?
If you sample them, you could hold those out for validation of most rare or important.
Yeah. So the broader technique here is maybe traditionally you'd be sampling the validation data uniformly at random, but you might place higher probability on the rare event data to oversample those for the validation set. And that would actually make them even rarer in your training data, right? So then you would really see how your model is going to struggle with those. Cool. So yeah, there's many other forms of selection bias that I won't get into, but just be aware that this in general is really, really hard to deal with, and it's something you should always be thinking about when collecting the data. So for the next topic, we'll ask the question, how much data should we collect if our goal is to achieve a particular level of accuracy? So say we want to achieve 95% accuracy. How much data do we want? And to estimate this, obviously, we have to assume we already have some data and we've seen some kind of trend, right? So here, let's assume you already have your standard training data set, let's say just classification data set of sample size n. And we want to estimate this question of how much data do we need from data of size n. Any ideas on how we might think about that? Yeah?
Is there stuff where you can like estimate generalization bounds based on the sets of data set you're training?
Yes, that's an interesting one. So one option is to use theory. I'm actually not going to write that. But yes, you can use theoretical generalization bounds. That is very, very challenging for most modern machine learning. They often will give you very conservative numbers. Many of them, if you're measuring the literal accuracy of a model, many of the generalization bounds will say the error rate is greater than 1, which is a very vacuous thing to report. So here we're going to focus actually on more empirical ways to do this, like practically. And so a simple way you can try and think about this is what if we train our model on a subset of the data and see how it performs, and then train it on a bigger subset. And so you can imagine you have training, say you have your training data here and your validation data here. And this is like, all the training data that you have. You can subsample, say, only this training data, like some subset, and train a first model. Then you can subsample a bigger data set, train a second model, and so on and so forth. And for each of these models, you can evaluate its accuracy on the validation data, right? And so that will give you sort of a plot that looks something like this. So say we subsample 10% of our training data, 20%, all the way up to 80%, 90%, and 100%. And so you would expect the accuracy to be much lower, right, at 10% of the training data, and then better as you've trained the model on more data, and then even better on 80% of the data, and on 90% even better, 100% even better. And the question now is, say our goal accuracy is this number up here. We're essentially trying to figure out, right, at which point we will hit that goal accuracy on this x-axis. What multiplicative factor will we need to apply to our sample size n to get there? And so one problem with what I've shown so far is that each of these training runs on a subsample of the data set is pretty noisy, right? Like especially if you're doing neural network training, it's very stochastic. It really depends on what precise subset of the data I happen to sample as my 10% of the data. And so a good way to deal with that is just to do this multiple times. And each time you would train another model. And so you would have, multiple models. Say we do it 4 times for each one of these sizes. You would get four values, sort of like this. Again, due to the stochasticity, which would actually, you would expect the stochasticity to go down, right, as you get higher fractions of your data set because things become more stable. And of course, for the full data set, you can only train one model because that's all you have. And then the idea is now you have all these observations of models and validation accuracies, and you can actually fit a machine learning model to try and do the problem of figuring out at what n will I achieve the goal accuracy, right? So what is one remaining problem here? Say we fit like a linear model or a k-nearest neighbors model, for those of you who are familiar with those, to do this prediction. Like what makes this prediction problem a little more challenging than a traditional machine learning task? Yeah?
It assumes that you can just get enough data, you could get your accuracy arbitrarily high, or you might have some noise in your process that makes it so you can't ever achieve that.
That's, a big challenge. And that's related to sort of the other challenge here, which is that we're trying to, so here's our training data, it's all between 0 and 1, right? But the actual scenario we're interested in evaluating our machine learning model in here would be like 3 times the size of the training data set or something like that. So it's a huge extrapolation problem. And most machine learning models that you would have learned in class are not very great at extrapolation. Like a k-nearest neighbors model will never extrapolate beyond the range that it's seen in its own training data. A linear model would always extrapolate linearly. And fundamentally, the only way to actually really do extrapolation well is to use knowledge. That's just, that there's no data when you're doing extrapolation, so you have to know something about how the world will behave as you get more data. And so this is just an empirical fact that many people have rediscovered. But roughly speaking, the error rate of these models tends to behave according to the following formula. And so here, these are just parameters that really depend on the application. But this is the sample size, and this is the error rate of the classifier on held out data after it's been trained on a data set of the sample size. And so what you can do is basically fit these 2 parameters to the data set that you've collected so far through your subsampling, just using a least squares type of approach, and you'll get a curve that looks something like this. And then you can just extrapolate out that curve, right, until it hits your goal accuracy. And if it never hits your goal accuracy, then you're in bad shape. Then you probably need to change something more fundamental about your data beyond just collecting more of it. Yeah, so does that make sense? Anybody have any questions about that? Cool. Okay, the final topic we're going to talk about is the setting of labeling data. So far we've been talking about how much data do we need, what are the concerns that I might have when I'm collecting my data. And the final remaining missing piece is where do I get my labels from? And so suppose we have a classification data set with images, and some of them are like of a person, and some of them are about like cars. And so to label such a data set, the most natural way that it's done in many applications where a human can look at the image and determine the label is to use crowdsourced workers. So for a task like this, you could just use any common sense human could do this labeling task. These might be medical images, in which case you might need doctors to be your annotators. But the broader idea is you would have multiple annotators. Let's denote them A1, A2, A3. Say we have 3 annotators for our data set. And so we just show each annotator the image that we want them to label and say the first annotator says this is a person, and the second one says this is also a person, and then say the third annotator never sees this image. And why might that be? They might have become an annotator in our data set later on, or we might actually be trying to save as much money as we can to get the most amount of data labeled, in which case it's kind of redundant, right, to have all the annotators label every single individual example. You can imagine there are ways to use a predefined labeling budget more efficiently by only having some annotators label each example. So here we might, again, ask the first annotator to provide a label for this image, and they might say, oh, this is a car. And maybe they're the only annotator that has labeled this image. And then we might have some more images. Another person, and maybe now we don't have the first annotator label it, but we have the second annotator says this is a person, and the third one says this is a car, and then maybe we have another image of a car, say it's a truck, but this is just a binary classification task, so this annotator, say all 3 annotators say this is a car. And so what kind of information can we start to see here? One thing we can start to see is that the first annotator is doing pretty well, right? They're giving the labels that most often seem to agree with the other annotators compared to the other 2 annotators. And this annotator is the one we should be most concerned about because basically this annotator has given an image a different label than another annotator. And so here we come to the question of how would you know which of these annotators is giving you good labels, which one is giving you bad labels? And furthermore, how would we deal with this image where we've only got one label, right, from one of the annotators? That's maybe we're not, it might be challenging to say we're very confident in the label for this image. And we might want to have some kind of confidence score for if we collapse all of the annotations into a single label for each of these images, we might want to know that maybe we're less confident about this one because it was only annotated by a single annotator. And so to introduce some notation here, we're going to denote these labels as y, I, j. And so this will be I here is the example, and j is the annotator. And these are either just empty if the annotator did not label that example, or just one class if this is a classification task. Okay, so beyond some of the annotators providing inaccurate labels, can you imagine another kind of challenge that might come up with your annotators? Like what other problems should you be thinking about before you go just start getting these annotators to label your data? Say you're paying each annotator for the labels they give you. Like what might be scenarios that can go wrong? Yeah?
They label faster to get more fit.
Yeah, so they label fast and they're not really looking at the image or thinking about it. So they're giving you sort of lower accuracy labels, right? That's a very common case. If you do like Mechanical Turk or things like that, you often see that. Yep?
Right now the assumption is that there's no collusion between annotators, so each one is independent, but that might not be the case.
Exactly. So that's a big problem. So the two problems, to recap, are one, that you just have low accuracy annotators, maybe because they're just trying to do this as fast as possible, and then you have copycats or collusions between annotators. Maybe one annotator actually made 3 accounts in your labeling platform, and they're getting 3 times as much money that way. And so the best way to diagnose these kind of problems is to actually insert sort of gold standard examples randomly into the data that each annotator is labeling, where you know what the true label should be, and then you can assess whether the annotators are agreeing with your gold standard, or whether when they're making errors from your gold standard, are there multiple annotators that always happen to make the same kind of error. And that's really the best possible way to deal with these kind of problems. Of course, that is challenging in its own right because it means you're now spending a chunk of your labeling budget having annotators label data that you already know the labels for. And so actually, this is unfortunately often not done in many data sets. And so for the rest of the lecture, we'll talk about in the absence of gold standard labels that each annotator has labeled a decent number of images where you're very confident you already know the true label. Sort of how can you still try and analyze this data and pull out estimates of interest. So I'll shift over here. And so yeah, given a multi-annotator data set, what are we trying to estimate from this data? The first thing we obviously want to estimate is just like what is the consensus label for each example. So this would be the label that we think best describes this example. So going back to our example here, certainly for this image, it would be quite crazy of us not to just say car is the consensus label for that image. Another thing we want to estimate is a confidence measure in these consensus labels, right? So how likely is it that the consensus label is correct or not? So going back to the confidence idea, for this example, intuitively, we should be a little less confident about it because there's only one annotator who's labeled it. Similarly, for this image here, we have two annotators that have disagreed. So no matter what consensus label we would choose for this image, we would kind of be a little cautious and not super confident that we have the correct consensus label, right? Because we actually do have two annotators who disagree. Versus in contrast to this final image here, we should be very confident that it should be labeled a car and that our consensus label probably is correct. And then finally, we would be interested in estimating a quality score for each annotator. And this would be asking, like, what's the overall accuracy of their labels, right? Okay, so can anyone tell me the most obvious strategy for estimating, a single consensus label for each example over here? Like, what would be your algorithm given just this data and let's imagine you don't even see the images, you're just given the annotations for each example. What kind of algorithm might you use to determine what's the best label? Yeah, so the simple approach is to do majority vote. And so here we're going to denote the consensus label as y hat I. And that's going to be our best guess for the true label for example I. And so the majority vote algorithm would just count which label is the most common for each example and say that is what we define y hat I to be. What might be a natural, if we are going to use majority vote as our method for establishing consensus, what might be a natural analogy of that to estimate the confidence in the consensus? Yeah?
What percent of the votes agree with the majority?
Exactly. So agreement between annotators is our score is our confidence score for how likely we think the consensus is correct or not. Okay. Oh, that was loud. And so using some notation here, if we let ji be the set of annotators that labeled a particular example, I, we can mathematically write this agreement as, for example I, as 1 over the size of this set ji, and then we just sum over all the annotators that did label example I and assess whether their given label matched our consensus label or not. And this is coming from majority vote. Cool. Does anybody have any questions about that? Yes?
Does this include the fact that our confidence should be lower when we have fewer labels?
So that's a good question. No, it does not, right? It's not at all accounting for that. It's just looking at how much do the people that did label this example disagree. And so that's exactly an issue with this approach, one of the many issues that I will get into. And then finally, if we wanted to estimate the quality of each annotator, again, doing a very simple approach like these two, how might you guys suggest estimating the quality of each annotator? Yeah?
How often do you agree with the consensus vote?
Yeah, So that would exactly be a very straightforward way to just estimate their quality. What's one challenge that comes up? Say we're doing this, using this data set, we've established the consensus through majority vote, and now we're going to score each annotator based on how often they agree with consensus. What immediately jumps out at you as sort of a issue? Yeah. Yeah, so some annotators did not label some examples, right? So we have to sort of not, like when we're evaluating the accuracy of this annotator, we have to not consider these two examples, right? What else jumps out at you? Yeah?
It really incentivizes copycatting.
Yes, that's an issue as well, because copycats are going to just be much more present in the data. And then another issue I want to point out is what about this example here, or trying to score this annotator where they were the only one who labeled this image. They sort of get a point because the consensus under majority vote for this image would just be car, and they're just agreeing with themselves, so they really shouldn't get a point for that. So that's just a bit of notation. That's a subtle point I will introduce here, which is that we want to define, can you guys see down here? Yeah, okay. We'll define this set ij plus as the set of annotators who have labeled example j. Let's just call it the set of j, such that yij is not empty. And there exists at least two annotators who have labeled oh no, sorry, this is going to be the set of j such that yj is not empty, and there exists another annotator j prime who has labeled the examples that this annotator has labeled. I need to use this eraser here. Okay, and so with this definition in place, then we can say that we evaluate the annotator quality under the simple baseline as just the agreement between this annotator and the consensus label over those examples that fall into the set. So I'll let you digest that for a second, but really the only subtle point here is the definition of this set is just to make sure that we're not like including, when we're scoring the quality of annotator 1, we're not including, the fact that that was the only annotator that labeled this example. So this example would not fall into that set ij plus. Okay, what's another downside of producing the, say, consensus labels through majority vote?
The same number of votes for the same label?
Yeah, so ties is another issue, very obvious issue that, and also like just the quality of the annotators is not being accounted for, right, at all. Like if this is a good annotator, that's a bad annotator, they sort of both get votes and they're equally weighted. So I'm going to just jump into a better method that can be used for analyzing such data. And so here, basically, what can we do to deal with ties? Ties are kind of challenging, right? One thing we can do is we can train a classifier on these images to do some prediction and use estimates from the classifier almost as if it was another annotator. So say we train a classifier. And it, predicts for the first image person with probability, say 0.8. And for the second image, it predicts car with probability 0.7. And for the third image, say person with probability 0.9. And let's say we just had trained this classifier, for example, taking majority vote of all the labels initially, and then training the classifier. So now that we've trained the classifier and gotten its predictions, how might we break, say, the tie for this image if we are now trying to establish a consensus label?
Like using the classifier's solution?
Yeah, exactly. We can, break ties based on the classifier. And why might that be a good idea? The reason it might be a good idea is because right now, if we're just trying to determine what's the best label just based on this information only, we're not relying on the pixels, like the actual features of the example at all. But maybe the data set contains a bunch of very similar examples to this one that have much higher quality annotations because maybe they were labeled by many annotators. And so the classifier can actually generalize, from a similar image to this image and provide additional signal. And so using the classifier to break ties is a very easy improvement already on just doing majority vote solely for the reason of ties. Another thing is the classifier can help us with these nasty singly labeled images where you just had one annotator who labeled the image. For those, you're just really relying only on that annotator, right? And so without anything else, there's not much you can do besides just take that annotator's word as your consensus label. But if your classifier, say, is extremely, extremely confident about that example because it's seen 100 other cars in the data set that all had the same label and they all looked very similar to this car, then maybe you say, okay, this one annotator said it's a car, my classifier is very confident this is a car too, and so I'm becoming more confident in the consensus quality for this example. I'm getting to time here, so I'll just go over the final part very quickly. But broadly speaking, a way we can get a better estimate of all three of these quantities is a method called CrowdLab that you will see in your lab assignment for this week, or for this lecture, I should say. And the idea of this method is that we are going to form a probability distribution of what we think the true class should be, just like you saw in confident learning, based on the features of the example, as well as all the annotations. And the way we will form this probability distribution is we will do it as a weighted average of all our annotators. We will allow each annotator, we will convert each annotator's label to a probability distribution, almost treating the annotator like a predictor, right? In some sense, that's what they are doing. They're looking at the thing and predicting what they think the label should be. Let's just call it like that. And then we are going to add on also our model's prediction. And we'll denote that by PM. And the model is conditioning explicitly on the feature values, right? The classifier. And what you'll notice here is that we have weights. And what these weights allow us to do is they allow us to downweight an annotator that is bad, right? Give that annotator less impact on the resulting estimate of what we really think the true probability of each class is for this example. And they also allow us to up or downweight the classifier based on how good do we think the classifier is relative to a random annotator. And that's a function of many things, right? Like the kind of data we're dealing with, how noisy all the annotators are, and other issues like and how many annotations we have per image. So even if you had really, really bad annotators to begin with, but you had 100 of them look at each image, and then you took majority vote labels, and then trained your classifier might actually be a lot more accurate than any one of these annotators. And so the idea of the crowd lab method is you will form this probability estimate of what the true class is for each example. And using that estimate, you can just take the consensus label as the most likely class, and the confidence just becomes the probability assigned to that most likely class under this estimate. And so in your lab assignment, you will see how we can produce these weights according to this crowd lab algorithm such that they properly account for downweighting bad annotators, upweighting good annotators, and accounting for how accurate the model is relative to each annotator. So, any questions? Yes?
If you were to run this iteratively on a data set, would you expect that how good the annotator qualities of your original annotators, would you expect all of that to converge?
Yes, exactly. So you can start with majority vote labels, train your classifier on the majority vote labels, compute this thing, then get new consensus labels and retrain your classifier on those, and yes, it will converge. And in theory, it can get better and better. It can also there's one challenge, which is if your model is really, really bad, then relying on the classifier can be dangerous, of course, because you're relying on this extra source of information that is potentially misleading. Yeah?
So this kind of overlaps, but for the classifier, are you training it just pruning out the data that you don't have a lot of information on, and just pruning out that?
Yeah, so I did not at all talk about how we train the classifier. So a really simple way to do it is just to take majority vote labels and train it on those, assuming those are noisy labels. And then you can apply all the techniques we talked about in confident learning in the prior lecture to try and say which one of those are noisy based on the classifier's estimate. Prune those, you could retrain the classifier, and then use that classifier. There's a lot of things you could try and do to build, but here we're just assuming you've tried to build the best classifier you can. Any other questions?
Wait, does that weight for the classifier change depending on the data points, or is it?
It's a constant weight. So you're just assuming the classifier is equally, it's just how accurate is the classifier relative to your average annotator. And the details of it you will see in the lab assignment. Yes?
Could you make something slightly more sophisticated where you maybe look at how good an annotator classifier is on a given class prediction?
Yes. That is a method I did not have time to get into, but there is a method, like Curtis showed that confident joint estimate. There's a method that stores something like that for each annotator and tries to estimate that. That is challenging though, because it really requires each annotator to have labeled a lot of data to really see how good they are at each class. Yeah. But that's actually how a lot of the classical algorithms in this space worked. Yes?
I guess to me, this seems a little bit circular
Mm-hmm.
in that we have these annotators to create a classifier, but we're using a classifier
To rank them.
Yeah.
Uh-huh.
Evaluate the annotators. So where do you start and where does it end?
Yeah, so you can just do this one time. If you just do, like in the lab assignment, you'll just do this one time. So you'll have a classifier, or you'll have just this data first, right? Then you'll form some kind of initial crude guess of what the best label for each example is. Train your classifier on that. Then estimate those distributions of the true class, and then just form a better consensus label based on that. But you could repeat the process again, and as formally asked, it will converge if you repeat it multiple times. As long as your classifier training is stable, of course. How stable the training of a classifier is very much depends on the classifier.
So converge means you get all of the labels correct in the end?
Converge just means the consensus labels will remain stable. They won't change anymore. Getting it correct really depends on a lot of conditions. Yes, if you have 100 annotators labeling each example, you'll see in this formula here that this sum here over the annotators will dominate then versus over the classifier, right? So for such examples, basically you would only be relying on the annotations. And if 50% of the annotators all said it was class 1 and 50% said it was class 2, you would immediately, this term would still dominate over the classifier's input. And you would see that this is just fundamentally a really hard example because I had 100 annotators look at it and 50 of them said this thing and 50 said another thing. Yeah.
Maybe one way I think, so Jonas created this method, and this on the left, it's just like, with working with some folks. But the way I think about your question is that the classifier is vertical. So the classifier gets more information because it can look at all the data and all the images, and then use all that information to get a good idea for each example. And then the other method is annotator-based, right, majority voting, and that is horizontal. So you have horizontal across the matrix, that's one, and then you've got vertical across the matrix, that's the other. And then this equation on the left is combining both horizontal and vertical. And so that's why they each provide different information, and additively you get more.
And you can keep iterating to do it multiple times. But you'll see, even if you just do it once, it gives you a lot better estimates than something like majority vote, because majority vote has so many problems like we talked about. Even just using the classifier to break ties in majority vote gives you something already much better due to having ties. Cool. Now with that, you will learn the details and see it working for yourself, hopefully, in the lab assignment. And I think we're over time, so thanks for coming.